Dear students, today we are going to discuss about an important as well as an interesting topic, that is weightlessness. This is a concept that fascinates many of us, especially the beginners. So to understand this concept, you need to know certain basic things in first. One is what is weight, what is mass, what is the true weight of an object, and what is the apparent weight of an object. Now, we know that weight is the force with which a body is attracted towards the center of Earth. So this is the center of Earth. The force with which a body is attracted towards the center of Earth is called as weight, and weight is defined as mg. Whereas mass is the quantity of matter contained in a body, quantity of matter. So we can say that mass is a scalar, weight is a vector because it is a force. If you have to find the mass of a body, obviously you will divide this weight by the acceleration due to gravity and you will get mass. Mass is measured in terms of kilograms, grams, tons, metric tons, and so on. Remember, all weighing machines and spring balances, etc., they measure the weight of an object. Weight, right? And when you divide the same weight with the acceleration due to gravity or with any acceleration with which the body is moving, you find the mass of the body. Again, I'm repeating that mass is the quantity of matter contained in a body. It is measured in terms of grams, kilograms, tons, or metric tons, while as weight is a force with which a body is attracted towards the center of Earth. Now, the question is, if the bodies are attracted towards the center of Earth, then why don't we fall through the floor? And why don't we exactly reach the center of Earth? The answer is that there are certain reactionary forces. Reactionary forces, because in the Newton's third law, you have read that action and reaction are equal and opposite. Whenever we impose a force, we create a force, another force is spontaneously created to oppose the action of the given force, and that force is called as reactionary force. It is because of those reactionary forces that we are able to balance ourselves on the surface of Earth. And we do not fall through the floor. We do not reach the center of Earth. Now, for example, if a person is standing on a floor, there are two kinds of forces that act on him. One is his own weight, that is mg. It acts always downwards, always downwards. And another is the reactionary force or the normal force that we denote by Fn or capital N, right? So this force acts normally upwards and it balances this weight of the body, right? So this is called as this is the true weight, and this normal force or the reactionary force is called as apparent weight of the body. And remember, all weighing machines or spring balances measure the apparent weight of the body and not its true weight. Remember. Now, when the body or the person is at rest, right, its weight is balanced by the reactionary force. At that time, this spring balance or the weighing machine is actually measuring the true weight of the object. True weight. Because this true weight is the same thing as reactionary force because the body is at rest. Therefore, in this particular case, the spring balances or the weighing machines are measuring the true weight of the body. But then the cases may arise when the body begins to move. Either it begins to move in a linear fashion or in a circular fashion, or it may go up or it may come down. So in all those cases, we have to find what happens to this reactionary force, what happens to this apparent weight. Now, an interesting example, a popular example in that context is a person moving in a lift or an elevator. In a lift or an elevator. So let's try to see what are the various kinds of cases that arise. So, see, when the person in the lift is at rest, it's at rest. Obviously, its weight mg will be balanced by the reactionary force. So, The spring balance or the weighing machine will show its true weight only. True weight. Suppose the man weighs 84 kgs, for example. So this is the true weight or the apparent weight at the time of rest. Now, if the elevator starts moving with certain acceleration, then there are further two cases. Either the elevator is moving up or it is moving down. Remember, for all downward motions, we will give a negative sign to the force, and for all upward motions, we will assign a positive sign. Now, we know that weight of the body always acts downwards, so it is minus mg. The normal force or the reactionary force always opposes this force, so it is always plus. The competition between these two will decide this force, the force due to acceleration of the system, of the lift or the elevator. Understand? So if the lift is moving downwards or the elevator is moving downwards, obviously it will be ma, the force will be ma. And because it is downwards, so it will be minus ma. And because, remember, we are experiencing our weight because of this normal force. So this normal force is mg minus ma, which implies that in this case, the weighing machine is going to show a lesser reading. Lesser reading. Because this mg factor got subtracted by this factor ma, where a is the acceleration of the lift or the elevator, right? Now in the second case, when this accelerator moves up, again we know that weight will always act downwards. The reactionary force will always oppose it, that is it will act upwards. And when the lift moves up with certain acceleration, the sign will be positive, that is plus. So what is this normal force or this reactionary force? It is ma plus mg. Therefore our weighing machine will show an extra reading. An extra reading. Therefore, suppose in this case, at the time of rest, the weight of the body was 84. Once it moves downwards, it is say 80, and here suppose it is 88. This is because this weighing machine is measuring the apparent weight of the body. And apparent weight is the result of many things. It is the resultant of the weight of the body and the normal reaction, right? And this the acceleration of the system in which it is moving, right? So similar is the case with the astronauts who are moving in satellites and orbiting the earth. They feel a kind of weightlessness. So let us first discuss one more case. For example, if the elevator is such that its cable breaks, so what will happen at that time? It will fall freely. Remember, when this elevator or the lift is in our control, we are able to lift it up and lift it down with certain acceleration, with certain constant acceleration. But suppose it so happens that the cable breaks and the lift begins to fall freely. At that time, its acceleration is not a, but it is g, acceleration due to gravity. We know that all bodies that are released from a certain height with a zero velocity, with no external force, they reach the earth with how much acceleration? G. Because you have done those experiments that if a light weight object and a heavy weight object are released from certain height, starting from rest, they reach the earth at the same time. You have read those things. This is because they are moving towards earth with the same acceleration, and that is acceleration due to gravity, and that gives you the concept of free fall. At that time, light-weighted or heavy-weighted objects will not matter. What will matter is that they have reached the earth with the same acceleration, that is acceleration due to gravity. Now, similarly, I'm telling you that if the lift is such that it's stable or it's controlled, it loses, it breaks, the lift begins to move down only with the acceleration due to gravity. In that case, what happens? We know that the weight of the body, again, it will act downwards. The normal force, again, will be upwards. And what is the acceleration of the system? It is mg. Again minus times because it is falling. Now mg and mg goes and is 0. So this gives a feeling of weightlessness. Remember, feeling of weightlessness. At that time, your weighing machine or your spring balance is going to show a 0 reading. 0 reading. But remember, it doesn't mean that your weight is 0. It is only a feeling, a sensation, but not a reality. So that means the concept of weightlessness can be described even when the force of gravity is there. Because some people think that when force of gravity is not there, when this field is not there, people will not experience it. That's not true. It happens even in case of the presence of gravity, right? So for the astronauts who are orbiting the earth in the satellites, what happens is that no external force is acting on them. No external force is acting. The only thing that acts on them is the tendency to fall towards the earth, right? So they are not moving in a lift, they are not moving up or down with certain acceleration. The only force that acts on them at that time is the gravitational force of earth. Therefore, this force is only mg. Their own weight is mg. The normal reaction is n. This normal reaction, therefore, n is equal to 0. So that gives them a sensation of weightlessness. But that's not true that they don't have weight. That's not true. They always have weight. A body always has weight. Because remember that space or cosmos is always filled with gravitational force. Even if we talk about the range of the forces, for example, if the range of the gravitational force of Earth is up to this height, but beyond this height, there will be a gravitational force of some other object in space. Space is actually filled with this gravitational field. Remember. So we should not say that it is due to absence of gravity that we experience weightlessness, but we should say that weight is always there. The body always has a weight, but we get a sensation of weightlessness because these two forces balance each other. Our weight and the force due to free fall balance each other so that the reactionary force or the normal force is 0, due to which we have a sensation of weightlessness. Otherwise, the weight is not 0. So I hope that gives you a fair idea of weightlessness. And these are two popular examples to explain this. One is the motion of an object or a person in an elevator or a lift, and another is the motion of the astronauts orbiting the satellites, orbiting in the satellites around the Earth. So that's all.